Day 4, problem 1. Evaluate the 6 trig functions at the real number t equals pi over 4. So we want to figure out the value of cosine pi over 4, sine of pi over 4, tangent of pi over 4, secant of pi over 4, cosecant of pi over 4, and cotangent of pi over 4. What the pi over 4 is in this problem is an angle. And to help us find these values, we can think of our angle being on an x and y axis that's built on a unit circle. So here if we had a circle on the y-axis and the x-axis, if the radius of the circle is 1, then that's called a unit circle. Now pi over 4 radians is equivalent to a 45-degree angle. So if this is one side of the circle extending to the right along the x-axis, a 45-degree angle or a pi over 4 radian angle comes up like this and touches the unit circle right there. That has an ordered pair that goes with it. You can look in the back of the book to find out that ordered pair. It's the square root of 2 over 2, comma, the square root of 2 over 2. Now each of these trig functions corresponds to that ordered pair. In the case of cosine, it's going to be the x-coordinate from that ordered pair, which is the square root of 2 over 2. So the square root of 2 over 2 is the value of the cosine of pi over 4 radians. If you were to do this on the calculator and you hit enter, it would give you a decimal on the screen. It's not going to give you this nice compact form like this. The sine is the y-coordinate of this ordered pair, and it's also the square root of 2 over 2. Tangent is y divided by x. If you take this number and divide by this number, because they are the same, it's going to turn out to be 1. Secant is the reciprocal of cosine. So if we take the reciprocal of that value, that means flip it upside down, it would create 2 over the square root of 2. And then let's rationalize the denominator by multiplying top and bottom by square root of 2. That creates 2 square root of 2 all over 2. And then notice how the 2's cross out, and we're just left with the square root of 2. When you have a number like 2 divided by the square root of 2, if you just recognize right away that it equals to the square root of 2, that can save you having to do this work here in the middle. Okay, now let's do cosecant. That's the reciprocal of sine. But when you flip that upside down, that again is the 2 over square root of 2 situation that we just had. So remember how that worked out to the final result of the square root of 2? And then last we have cotangent. That's the reciprocal of tangent. The reciprocal of 1 is still 1. Now day 4, problem 2. Find the following sum. The expression that we're summing is 10 minus k. We're going to start by inputting 1 for k, and then input 2, 3, 4, and 5. We're going to stop when we get to 5. So we have 10 minus 1. That's the first term of our sequence of numbers, plus, and now we're going to have 10 minus 2. There's the second term of the sequence of numbers, plus, now 10 minus 3, plus 10 minus 4, plus 10 minus 5. And we're going to stop there because this expression says to go from k equals 1 to k equals 5. Let's simplify this out a little bit. 10 minus 1 is 9, plus 10 minus 2 is 8, plus 7, plus 6, plus 5. So we want to add up this arithmetic sequence of numbers. 9 plus 8 is 17, 7 plus 6 is 13, 17 and 13 is 30, plus 5 is 35. Just one comment on extension on this problem. You probably recall the other set of bellwork problems are about summing the terms of an arithmetic sequence. That's what we have here, an arithmetic sequence with a common difference of -1. Remember the formula was that the sum of 5 terms would be equal to 5 terms divided by 2 times the first term plus the last term. If you work this out, you happen to get 35. So it's interesting how this one turned out to be very connected to the problem from set 2.